let's begin. I want to continue with interpolation. Hopefully we should finish the whole thing by Thursday. I want to continue from where we left off last time. If you remember, we were working with this data set for temperature, density versus temperature, right? We had the data, we had this notebook with gaps. Just make sure you go ahead and open it. And if you remember what the data looked like, we had we plotted the density versus the temperature of density of air versus temperature. And it looked like this, went down, and we were asking questions about how to interpolate using straight line interpolation between every pair of points on this graph, right? And we went and used the interp function. We already developed the formula. We know how the formula works. We're not going to apply the formula here. There's built-in mechanisms in Python to do that. So we will just use those for now. And we talked about plotting, how to connect the dots. So this will give you an idea of how these straight line interpolants would look like. And we did a few interpolations to find the density as a function of density at different temperatures. If you remember here, we did it for 132 Kelvin. And here we did it for an array of temperatures. And the interp function in Python is great because it takes in a single value. It takes in a NumPy array. And then you can do a whole lot of interpolation at the same time. OK? And I showed you how you could show the interpolated points. And one thing we did at the end was we created a lot of new points. So the discrete data that's given to us are those black disks, right? And then we said, OK, we're going to interpolate a lot of points in between those discrete points that were given to us. And excuse me, we went ahead and did that with a lin space. We created a space of points and temperature from 100 to 1,000. We put 100 points for temperatures and interpolated using the input data. And the interpolated data is shown here in red. And what was unique and what we stressed about last time is that if you interpolate to a given data point that from the input points, then you're going to recover the input value. Because by definition, that's how interpolation worked. We weave the interpolating function, these straight lines, we weave them between the input data points. So it's a necessary condition that the interpolant, whether linear or later we're going to learn higher order interpolants, it must pass through each and every input data point. So if you ask the formula to give you the interpolated value at one of the input data points, it's going to give you the input data point, okay? The y value at the input data point. Just like this guy over here, that guy, this guy, all of those, okay? You can verify that for yourself. All right, and I showed you here like the input value for 150, which is exactly the inputted value from the discrete data. Okay, so now I'm going to pose a question which will often arise, and that will kind of turn things over. We always distinguish between the dependent variable and the independent variable. Oftentimes you choose, oftentimes you have no choice in the independent variable, like space and time are always almost independent variables, okay? But sometimes you could ask the question, at what time is the concentration? So let's say you're measuring concentration of something, of a reactant or air pollution over time. But then you can ask the question, at what time does the concentration reach a certain value? In that case, you've flipped the meaning of independent and dependent variable. Now time became the dependent variable, and the concentration became the independent variable. Okay? So that thing can happen in practice. And here is one example of this. So far we've treated rho, the density, as the dependent variable, and T, the temperature, as the independent variable. And this poses the question here. Suppose now that we want to find the temperature given a certain density value. For example, what is the temperature at which the density of air is 2.3364 kilograms per cubic meter? Right? At what temperature does the air achieve that density? Right? So we've inverted the meaning, density versus temperature. Now we want temperature versus density, right? We've kind of flipped that graph, okay? The tabulated data should return t equal 150 exactly. Okay, so if you look at the tabulated data, at t equal 150, you get 2.3364, right? So that's the density array, and the temperature array starts 100. The next value for the temperature array is 150, right? So this second value corresponds to this value of density. Okay. So now the question is, okay, can you do this with interp? Okay, now use the interp function to calculate the temperature for a given density. So now you've swapped, the meaning of dependent and independent variable. Okay? If you don't remember what the interp function does, you can look it up in the slides. I'll show it to you briefly over here. Okay. So in the interp function, this is where you want to interpolate to in terms of the independent variable. Xi is the input independent variable, and yi is the input dependent variable. Now we've swapped the meaning of rho and t. Okay? In this case, rho became our independent variable, and t is our dependent variable. Okay? So go ahead and try this. Let's see what you get. So those question marks. Yeah, I'll give you the first one. We want to find the temperature at a density of 2.3364. Agreed? So now what goes here? Remember, the input data is given as rho and t. Yes? And for yi, t. Yep, we swapped the meaning. Okay. So try it. What did it give you? 1,000. Gretchen? 1,000. Did you get, Nicholas? 1,000. 1,000. 1,000. 1,000. Good. Does that make sense? So 2.3364, if you look at the graph again, is just around here. And the temperature should be 150. So what the heck is going on? Why is it giving us 1,000? So I'm going to put rho and t. Okay? So there's clearly a problem over here. So let me explain what's going on. Where is the... Okay. To use the interp function, if you're doing this by hand, it will just work. You'll pick two data points around that density value. You swap the meaning of t and rho, and you can apply the formula. It will work just fine. Okay? But for the interp function, because you're giving it like a full array, the full range of data points, you're giving it the entire range of data points, you need to make sure that the independent variable is sorted in increasing order. It has to go from small to large value. Okay? So you have to sort it that way. So you have to make sure that's the case. Now, if you notice in our data, that's not the case because let's print rho. Okay? So rho is not sorted in increasing order. Rho is sorted in decreasing order. So when we swap the meaning, rho became the independent variable. Rho is not sorted in increasing order because that's how the data came into us, right? So before we use interp on this data, we need to make sure that the independent variable is always sorted in increasing order. Okay? So we need to do that. But not only that, you need to also make sure that the new dependent variable is mapped correctly, because if I sort this, if I change the sorting on this, I need to change the sorting on the temperature as well. Because this value corresponds to 100, this value corresponds to 150, this value corresponds to 200, and so on. If I reverse the order of this, I want the temperature array to still map correctly one-to-one to this. So if I sort this, I also need to sort the temperature array. Okay? Does that make sense? Because for every value of temperature, there's a density. You change the order of the density, you need to change the order of temperatures in the temperature array accordingly, so that the values, they still match, so that they're still data pairs. There's a couple of ways of doing this in Python. Okay? And the most generic way, because I will give you this in the homework. And in the homework, I'm going to give you an array that's not even sorted at all. Just arbitrary numbers are scattered. Large value, large value, smaller value, etc. Right? You still need to sort that array, and you need to sort the dependent variable array accordingly. Okay? So the most generic way to do this in Python is called argsort. It comes from NumPy, and argsort starts for argument sort. And what it does, it returns the indices that would sort an array. So what that does, it's kind of interesting how to think about it. So let me show you an example. Okay. Let me show you an example. Suppose that A is np dot array. And I'm going to put 1, 3, 2, 5. Okay. Now, to sort this in increasing order, we need to move 2 over here and 3 over there, right? Well, let me spice it up a little bit. I'm going to go 5, 1, 3, 2. Okay? So to sort this correctly, this guy at index 1 needs to become index 0. This guy at index 0 needs to become at index 3. This guy at index 3 needs to become at index 1, and so on. Okay, so argsort will do that for you without even blinking an eye. So let's see what it does and reason about it. Let's say sorted indices equal mp.argsort A. Now, if I print sorted indices, print sorted indices, what it did, these are the indices of these values that would sort this array. Okay? These are the indices that would sort this array. Now, how this works, let me show you. Now, if you go and say A of sorted indices, it sorts it for you. Now, why is this powerful? Let me move this back down here. Okay. So if you go to numpy.argsort, it returns the indices that would sort an array. So essentially what this is saying, it says that index 1 in the original array should be the first entry. So it's going to take this value, index 1, put it here. Index 3 should be the second entry. What is index 3? 0, 1, 2, 3. Then 2 is going to be the second entry. Index 2 should be the third entry. 0, 1, 2. So 3 should be in the next entry. And index 0 should be at the last entry. So 5 is at index 0, is going to be at the last entry. Now, why is this very powerful? Because when I get the sorted indices, I can apply them to the other array as well. Because both arrays, they came in matching accordingly, one-to-one correspondence. If I sort the density array, I need to sort the temperature array accordingly. If I sort the temperature array, I need to sort the density array accordingly. So all you have to do is get the sorted indices and apply them as needed. And once you do that, it will just work. So this would work for an arbitrarily rearranged array, and you'll sort the other array accordingly. And so that will be in the homework. I'll give you an array with jumbled data. I'll ask you, okay, interpolate treating density as independent variable, temperature as dependent, and then swap the meaning. So you have to do this on both ways, okay? Okay, I know kind of the argsort is kind of weird index, and like, even for me for a minute, like, what are these indices? What this is saying is that index 1 in the original array, the entry at index 1, which is this guy, should be the first entry in the new array. The entry at index 3 should be the second entry. So 0, 1, 2, 3. So 2 becomes the second one, and so on. Okay? So that's how that works. Okay. So then you see how I've done it here. Sorted indices, or IDX, we're going to sort the density array. And then we sort it this way. And we will also need to sort the temperature array accordingly. So now here's what happened. When we sort the density array, we're starting from the small values all the way to the large values. But then automatically, the temperature array has automatically been resorted so that you get the correct matching between temperature and density. And now when you go ahead and apply the interp function on the 2.3364 and give it the sorted density and the new temperature array, then you're going to get 150, the correct value. It's a very important concept when you're using interp. If you're doing by hand, you have only two data points. You just choose which is x and y, and you apply the formula, it will just work. But this is only an issue for the interp function when you're applying it for a large data set, or even just 2 points. The independent variable needs to be sorted. Whatever you're treating as the independent variable, you need to sort that. Then you sort the dependent variable, the dependent array accordingly. Because you have to make sure the order they're still matching. For every temperature, there's a density. For every density, there's a temperature. Okay? You need to sort those consistently with each other. Okay? See a lot of squints, and takes a minute to absorb the concept, but it's a very, very useful concept. There are a couple of NumPy routines that would sort an array, like mp.sort would sort it in increasing order, but that's not useful for us because we also need to sort the other array. What if the other array is not necessarily going to be in increasing order, right? So the arc sort is still the best one because it gives you the indices of the sort that needs to be sorted. Flip upside down, it flips an array upside down. It sometimes happens that you have an array in decreasing order anyway, so you just flip it upside down, and you flip the other one upside down, for example. And you say, that's a victory. I always use this one. Okay? I don't worry about playing games with this. I always use this one. This is robust and bulletproof. Okay? All right. So we've done, so far, interpolation to a straight line. And notice how I'm changing now my words. I used to, last Thursday, I used the word linear interpolation. Okay? And that's not incorrect. But I want to be more precise, and I want to use the word saying interpolation to a straight line. Because we will mean eventually in this class, we will designate linear interpolation to mean something different. Okay? We will see that even complex functions, we can call them linear interpolation procedures. We'll cross that bridge. Future us will cross that bridge. But for now, notice my nomenclature change. Interpolation to a straight line. It's not ambiguous. Nobody's going to argue with you about it. Just interpolation to a straight line. You're very clear and precise. Okay? So far we've done only interpolation to a straight line. But you might ask, could we do a quadratic, for example? Could we do a cubic? Could we do higher order polynomials? Indeed, we can. And we'll start with the definition, making sure and reminding you that an interpolating function, so that straight line or any other thing we're going to put to interpolate the data, is by definition must pass through each and every point of the input data. That's a necessary condition for interpolation. So if you think about these little diagrams that you would do in the Scouts, you'd have like these pins on a board, and you start putting twine in between them, right? So you anchor the twine at each one of those pins, right? So that's what you think about interpolation. The input data points are going to anchor the interpolating function or the model you're using. Okay, so let's see how we can do higher order interpolants. It's really straightforward once you see this example. So when we were given two data points, we put a straight line between them, because that's kind of the obvious thing you could do, just draw a line between two data points. And it worked so well because for the equation of a straight line, in this case, you have two unknowns, the slope and the intercept, right? So a1 and a0, if you take that model formula, y of x equal a0 plus a1x. So, and remember here, x in this case is not an unknown, because our unknowns here are finding the slope and the intercept. What does that straight line look like between any two data points, right? So we've swapped the meaning of what the unknown is. And in this case, we ended up with a system of equations, and the unknowns are a0 and a1, the slope and the intercept for that straight line. And this is how you build it. We solved it analytically last time, and we came up with that little formula, back of the envelope method of doing linear interpolation to straight line, and that works fine. Okay, so that worked with 2 points because we had two unknowns, right? So you need one condition for each unknown. You have two unknowns, you need two equations. Those two equations come from making sure that straight line goes through point 1 and point 2. That's why I stress on the fact that an interpolant must go through each and every point, because as it goes through each point, that gives you a condition. So you say y1, the interpolant at x1 is equal to y1. The interpolant at x2 is equal to y2. So you get two equations. You have your two unknowns, a0 and a1, and then you can solve the system, okay? So in this system, x1 and x2 and y1 and y2 are known values, all right? So now, if you're given 3 points, could you do something a little bit more advanced? You could probably fit a quadratic. Why? In this case, a quadratic has 3 coefficients that would be unknown in this case, right? So what does the quadratic look? What are the coefficients of this quadratic? But it must go through those 3 points, right? Okay, so given these 3 data points, I want you to go ahead and derive the system of equations that governs a0, a1, and a2. So what equations do we need to solve to find a0, a1, and a2? Similar procedure as the straight line, except now you have a quadratic. Okay? Grab your pen and paper and start working. And you can work together as usual. Kind of always that idea of groups starts nice at the beginning of the semester, but then it just all breaks apart. So write the equations first, and then put them in matrix form. Remember the condition that any interpolant function must go through each and every point. So that gives you your conditions. You have 3 unknowns, and you have 3 points. Great, just write them down. Pass that quadratic through each and every point. So the quadratic must pass through x1, y1, x2, y2, and x3, y3. So do it similarly to what we did with the straight line. So check the work. This doesn't make sense. Right? It won't multiply the matrix, the coefficient matrix. And I really encourage you to write the system before writing the coefficient matrix. So pass that quadratic through x1, y1, x2, y2, and x3, y3. Beautiful.
Just
Perfect.
putting it like
Beautiful. Yep, yep, yep. Yeah, right. Finish up the matrix form. Bravo. Yep. So how did you come up with this?
Oh, I'm writing it down. I just use the equation up there. And
Yeah.
then
Yeah.
I know that we have different
So-
values back, so we need 3 values.
Yeah. Yeah. I will just caution you before you jump to the matrix form that I can trick you with this, and I will trick you in the exam.
Okay.
And it will break this. So write them down.
Okay.
Right here, so I wrote out the system of equations, which is right.
Yep.
I'm
Perfect.
just pulling out the x1, x2, x3. and then
Right?
this
Yeah,
piece.
because x1 and y1, x2 and x3, y2, y3, they're known values. They're just numbers. You need to put the unknowns in the column vector, right? And the matrix has the known coefficients. So you got it right. Yep. Yep. You got it. You got it. So now do it for a cubic. That's inconsistent with this, right? What about the x1 squared, x2 squared, and x3 squared?
Oh, yeah.
Yeah, so they should go, yep. And you have a2 as well, right? Yeah. Okay? Okay? Good? Good? Good work. What is y0 or y3?
What?
Where is y3? 0. Okay. Okay? Awesome. So, I walked around and I saw most of you got it. So let's do it together. So here's my general formula. So I have 3 points, x1, y1, x2, y2, x3, y3. Forget about that red line. These points could be anywhere. Then I want to pass a parabola between those points. It's going to look like this. Okay? Okay? I have the general formula for that parabola, but I don't know the coefficients, a0, a1, and a2. We're after those coefficients. Now, because I know that parabola must pass through each and every point, that gives me enough information to find a0, a1, and a2. I have 3 unknowns. I need 3 equations. It's great. I pass it through the points. At point 1, I know that y1 must be, that the parabola must go through this point. That means a0 plus a1 x1 plus a2 x1 squared equals y1. Right? Okay. Same thing for point 2. I know that the parabola must pass through point x2, y2. So therefore, at x2, a0 plus a1 x2 plus a2 x squared equal x2 squared equal y2, right? Just plug and play, right? Plug the x in the formula and make it equal to the y value. Same thing for y3. Okay, that's your system of equations. Okay, the unknowns, I'm showing them in red here because I want to stress on the fact we change the meaning of things here. The x values are known numbers, x1, x2, x3, y1, y2. They're all known values. The unknowns are the coefficients in this case. And I encourage you to write it in this form before you jump to matrix form. I know the matrix form is going to look like, oh, yeah, it's recursive. It looks like this for a straight line. It looks like this for a quadratic, for a cubic. But I can break that with one example, okay? So make sure you are able to write the system of equations first before you write it in matrix form, please. Okay. So now I'll ask, is this a system of linear or nonlinear equations? Nonlinear? Linear? Okay, let's take a vote. Who says this is a linear system of equations? 1, 2, 3, 4, 5, 6, 9. Like almost half the class. Who says it's nonlinear? Okay. So why is it linear? Can we have the linear group? Move, everybody. So can I have a representative from the linear group say, first let's start with the nonlinear group. Can I have a representative from the nonlinear team to say why the equations are nonlinear? Michaela? You're with the linear group. Okay. Okay, what about the nonlinear group? I want someone from the nonlinear group to say why the equations are nonlinear. Did you change your mind? Daxton. Okay.
I would say why I thought it was nonlinear, but I changed
Go
it
ahead.
now.
You
I
say.
thought the x's were the unknown, so I thought they would be squared. However, the a0, a1, and a2 are.
Right. The x's are just going to be numbers. In practice, once you have the data, x1 squared could be 2.3, right? It's just a number. Right? The fact that it's squared is a trick. It's there because I don't know what x1 and x2 and x3 actually are, but they're just given numbers. They're input numbers that you know that you're going to plug in these equations. Once you put the numbers in there, this is just a linear system of equations in the a's. But even if you didn't know that, just ask yourself, what are we after in this system? We're after a0, a1, and a2. How do they show up? As your colleague said, they show up linearly. They're not squared. They're not under a transcendental function or any trigonometric function or anything like that, right? Even if one of them, if one term had a transcendental operation on it, the whole thing would be nonlinear, okay? But it's not, thankfully, okay? Now you translate this into a matrix form, and lo and behold, you get a system of linear equations. You invert this, do numpy.linalgebra.solve if you want to do that, or we will just use built-in functions, routines in Python. Okay, so let's see where we're at. When we had two data points, we could fit a straight line because we had two unknown coefficients in the equation for the straight line. I want you to think of the straight line or the parabola as a model for the data. You stand there, you look at the data. This data looks parabolic. No. This data looks cubic, right? What you did there, you've assumed a model. You've modeled the data. You said you made a choice that I want to model the data as if it's a straight line, linear. Or I want to model it as if it's behaving quadratically, like a bunch of parabolas. That itself is a model. So now I'm going to call this interpolating function. We'll use it interchangeably. We'll also call it an interpolation model. It's a model of the data. Okay? It's a model for the data. And that will be helpful when we hit regression. Okay, that nomenclature. Okay, with 3 points, we could fit a quadratic. With 4 points, we could fit a cubic. Right? So how many unknowns would there be in the cubic model? A0, A1, A2, A3, so 4 unknowns. Right? We're after the coefficients. Remember that cubic is going to go through those 4 points. That's where we get our 4 conditions. Then, if you go and generalize, for n plus 1 points, you get an nth order. You can fit an nth order polynomial. So for 10 points, you can fit a polynomial of order 9. For 100 points, you can fit a polynomial of order 99, right? Because you have this many unknowns. Okay? So you need n plus 1 unknowns, obviously, right? Because you have the a0 here that's not powered. Okay. So in general, you could fit a general polynomial through part of or an entire data set. The a's are the unknowns, and we have n plus 1 unknowns. We need n plus 1 equations, and therefore we need n plus 1 points. Okay? Now, in general, you say for n plus 1 data points, we can fit a general polynomial of order n at most. Okay? At most. That's the highest order you can do. Now, remember, a polynomial of order n, a general polynomial of order n has n plus 1 unknowns because you have the a0 and then a1, a2 all the way to an. Okay? So it still has n plus 1 unknowns. Remember, an interpolating polynomial, by definition, must go through each and every point of the data used to build the polynomial. Okay? So how do we get the system of equations that governs the coefficients? The same way we did for the straight line or the quadratic. We're going to take that long polynomial and apply it at point 1, point 2, point 3, point 4, and so on. You can systematically do this if you write the polynomial generically as this summation a naught plus a1x plus a2x squared plus a3x cubed and so on, and you apply it on those split data points, you get this system of equations. And you see now that matrix emerge, coefficient matrix. For a straight line, it was 1x1, 1x2, right? For a cubic, it was 1x1, x1 squared, 1x2, x2 squared, 1x3, x3 squared, and so on. And same thing, it just generalizes this for an arbitrary ordered polynomial. Okay? Now, this might sound daunting, etc. We're going to do it in Python, and we're going to say this is all useless. Okay? And we'll see why in a minute. Any polynomial, we will find that any interpolating model higher than order 3 is going to be rubbish. It would be foolish to use very high order polynomials, and we'll understand why in a little bit. Okay, so to do this programmatically, you obtain, first you solve this system of equations to obtain the coefficients of the polynomial, a naught, a1, all the way to an. So you first find those coefficients, and then you create a routine that implements those coefficients in a polynomial function. So do you want a cubic? You have to write a code that says return a naught plus a1x plus a2x squared plus a3x cubed, so that you evaluate your interpolation model at any point that you want. Okay? So this is going to occur in 2 steps. When we did interp for the straight line interpolation, we just did interp, it did it for us, everything was great. But now for higher order quadratic or higher, we have to do it in 2 steps. First, we need to solve for the coefficients, a naught through an, whatever n is, could be 2, 3, 4, whatever order we care about, and then evaluate it, okay? And we will do this in Python, so now there's more tools that you're learning. So it would be nice if we could actually summarize all the tools we've learned in Python from the beginning, you know, NumPy and algebra solve, fsolve, etc., mat, pyplot, and etc. So there's, we learned interp, and there's a couple more that you will need to do high order polynomial interpolants. Those also thankfully come from NumPy, and they are called polyfit and polyval. Polyfit is the first step that I showed you. It's the step that takes input data, okay? It takes the input data and finds the coefficients for you, a naught, a1, a2, and so on. Polyval takes the coefficients and evaluates. Polyval is value of the polynomial. That's what it stands for. It evaluates that polynomial. So you give it 3 coefficients, it's going to assume that that's a quadratic, a naught, a1, a2. You give it 4 coefficients, it's going to assume this is a cubic and evaluates it for you. So here's the synopsis. Starting with polyfit, xi is the vector of independent variable inputs. Yi is the vector of dependent variable inputs. So temperature and density, or density and temperature. Degree is the degree of the polynomial that you are trying to fit. For now, make sure that if you have n plus 1 data points, you put n in degree. If you put anything else, you won't get interpolation. You'll get what we call regression. We will deal with that in a couple of weeks. But for now, for this lecture, for this week, in degree, if you have 10 data points, you put 9 over there. If you have 5 data points, you put 4. If you have 70 data points, you put 69. Okay? That's, just take that for granted. So you can do interpolation. If you put any other value for degree there, you're going to get regression. Why? I can't explain it now. We have to wait until a couple of weeks to explain regression. Now what this does, it returns the vector of coefficients of the polynomial, and we store it in P. Now the order of those coefficients is going to be an minus 1, all the way to a0. It just returns an array of those coefficients. But in that order, it starts with the last coefficient all the way to the first one. Okay, so polyfit would return the coefficients of the polynomial fit. Once you have the coefficients, now you have to evaluate the polynomial at different points. Then you use polyval. Now, the benefit of polyval is that, like I said earlier, if you have those coefficients, you would have to go and write your own Python routines to evaluate a cubic, a quadratic, a quintic, etc. Polyval does that for you automatically without you having to write any routines. Okay? So if I ask you in the exam, why do we need polyval? Because it circumvents the need of us having to write our own routines for polynomial interpolants, right? Okay? So polyval allows you to take a set of coefficients, these an minus 1, etc., and evaluate the polynomial at point xe. Okay? Now, polyval assumes that you have a full degree polynomial, that you have a0, a1x, a2x squared, a3x cubed, and so on. Sometimes you might have a polynomial that looks like a0 plus a3x cubed. Polyval can't do that. You have to write your own. Okay? In fact, polyfit cannot even do that. You would have to write your own system of equations and solve it. Okay, that's how I can break that matrix, essentially, that system of equations. But for these, where you assume a full degree polynomial, all the coefficients are there, no term is missing in your model for the polynomial. Okay, okay. So now we're going to go back to our density and temperature data. And one last point here. For n plus 1 points, if you choose a degree less than n, then you will get what we call regression. Okay, and we'll explain that later. It's no longer interpolation. It's called regression. It's an entirely different animal. Okay? So now let's see how this operates on the temperature and density data and kind of demonstrate that it's a foolish idea and a bad idea to use high-order interpolants for general data. All right, so we'll go back to the notebook. And we come here at polynomial interpolation. Now, let me ask you this. Is interpolation to a straight line also polynomial interpolation? Is a straight line a polynomial of degree 1? Yes, of course. Straight line is a polynomial of degree 1. A constant is a polynomial of degree 0. Just definitional, things. But okay, so a straight line is still a special case of a polynomial interpolation. Okay, it's just a polynomial of degree 1. Okay, so now we're going to attempt to do polynomial interpolation on the density and temperature data set. Let me zoom in a little bit. Poor guys in the back, they're buying binoculars just to see. Hold on. Okay, the back. Okay. All right, so from NumPy, we're going to import polyfit and polyval. And the first step is to obtain the coefficients. Okay, so what does polyfit require? You can go back to my slides here. It requires the input independent data, then the input dependent data, and the degree of the polynomial. So now we're going back to density versus temperature. So my temperature is the independent variable. My density is the dependent variable. Okay, and we need a degree for our polynomial. Okay, so try to figure this out. Give it a shot. What do you put in the first question mark? So remember, we have t and rho as our input data. I'm treating t as the independent variable and rho as the dependent variable. Okay, the first question mark, what should we put there? T, okay, T. All right, let's put T over here. Okay, and the second entry, Row. Very good. Row. What about in the last entry? The degree of the polynomial. Let's go count the data points. 1, 2, 3, 4. Or is there a cleaner way of doing this? So for n plus 1 points, pardon me?
I was just going to say the length of your array minus 1.
Okay. That's the correct answer. So you could count the data points, and that would be foolish, because if I give you 1,000,000 data points, or like 1,226,000, right? You're not going to count those. You just grab the length of that input array. That gives you your n plus 1 points, and minus 1 to get a degree n, right? So for n plus 1 points, we can fit a polynomial of degree n, or in other words, for n points, you fit a polynomial of degree n minus 1. So let's just put length of t. So we could do len of t minus 1. So that's your degree. Now, what is that? We can, if you're in doubt, we haven't said that in a while. When you're in doubt, print it out, okay? It's going to be a polynomial of order 18, an 18th degree polynomial. So it's going to have x to the power 18 in it. X to the power 18. Okay? All right. So now you run this. It's going to barf at you. Forget about it for a minute. I'm going to come back to this warning. It tells you polyfit is poorly conditioned. That's part of why high-order polynomial interpolation is a bad idea. But forget about this warning. It's just a warning. Okay, now my question, what is stored in coefs over here? What are we storing in coefs? What are we storing in coefs? Yes, Aaron? Yes, in what order? No, the opposite way, right? It stores them in reverse order. an minus 1, and so on. Okay? So let's see. You can print it out. So you can type coefs. Oops. Coefs here. And you just have a bunch of coefficients. The last coefficient is 5.83 times 10 to the power minus 46. Speaking of, that's below round-off error. And now you'll understand why this is a big issue. Why is such a small coefficient? Because that's the coefficient multiplying x to the power 18. If you do like 1.01 to the power 18, it's almost infinity, right? So the coefficient is really small to compensate for that large value in x. That's why you have a problem. X to the power 18 is going to be a very large number. Anything that is larger than 1 is going to be a large number, x to the power 18. So it compensates for that with a very small coefficient, right? And as you go through the powers, this is a naught. Okay, it's a normal number, minus 742. And this one is 35, right? This one is minus 0.77, etc. for x squared. But all of these higher order, 8x to the power 18, to the power 17, to the power 16, and so on, they're very small coefficients to compensate for the large value that's going to come from x to the 18, x to the 17, and so on. Okay? All right, so now let's see what happens. Let's evaluate the density at t equal 412 and 415. So now we're going to come back to polyval. Okay? So polyval, what does it do? Give it a shot here. You have the coefficients. Now you give the coefficients to polyval and tell it to evaluate it at a couple of points. Okay? So let's see. So in this case, I want to evaluate the density with these coefficients that we just computed, but at 412 and 415. And the same way with interp, you can evaluate at a single point or an array of points. What'd you get? Okay. Okay. So those are densities. Check do a self-check on the plot. Make sure that those numbers make sense. Okay. Did you get it? Somebody got it? No. You got similar values. Okay. Check if they make sense. Show me your polyval, please. Polyval coefs. Yep. Thank you. Okay. Okay. So let's do it. So we want to evaluate the density at a couple of temperatures, 412 and 415. So I'm just going to put those values as a list here. And the first argument in polyval are the coefficients of the polynomial. So I put coefs here. Now, what is polyval going to return to me? It's going to return two densities, two values for the density. The first value is the density at 412. The second value is the density at 415. Okay? Let's check that. Okay, I got 0.847 and 0.841. Does this make sense? Let's go do a sanity check. We're going to go back to the plot here. We had 412, so we're sort of around here. Okay? And we're somewhere here in this range. And indeed, the densities are less than 1. So they are between like 0.7 and 0.9. Yeah, that kind of looks okay. Okay, good. Good job, Mr. Polynomial Interpolant. Okay, so now let's go. Now evaluate the density at 980 Kelvin. So do the same thing with the same coefficients. You already have the coefficients for the polynomial. But do it for 980K. You have an answer? And does it make sense? Okay. Negative 0.4? Okay. Do you need to even look at the plot to know that this makes sense or not? Why? There's no negative densities, right? This is like an alternate universe. Okay? Did everyone get a negative value for the density? Yeah. You got a negative value. Okay. So let's see. Let me see if I can get a negative value. I'm going to put coefs here. Oops. And then 980. And bam. Minus 0.407. Okay. So what the heck is going on here? This doesn't make sense. We're supposed to do interpolation. That data point should be between. So if we go back to our plot here, as we go to 1,000, so the smallest value is like 0.2. So it should be around here. It should be like 0.23 or something. Why the heck did it give us a value like that? How about we plot this interpolating polynomial? We have everything we need to plot it, right? So we have the coefficients. We know the formula. I'm just going to generate a lot of points between 100 and 1,000 Kelvin and plot like we did with the interpolation to straight line, those red points. Okay, so let's go ahead and do that. Okay. So I'm going to actually copy this over here and bring it down. Okay. So let us plot the 18th order polynomial interpolant. Oops. Let's see what is going on. Okay. So I copied and pasted. Now my new data are going to be from 100 to 1,000. I'm going to put 200 points between 100 and 1,000. We can put however many points you want, but I want a lot of data points in between to really capture the behavior of that polynomial. Okay? Okay. So, and then what we need the y values are going to be polyval given the coefficients and at all the xe values, right? So xe is now my new set of points that I want to interpolate to. It includes the original points, and I don't care. Doesn't matter because I know it will give me the same input value. But I want more values in between those input points. And then I'm going to evaluate the polynomial, for which I know the coefficients. I'm going to evaluate it at all of those new points. So I can plot it, and so that it looks nice. Okay? All right, so we will we will plot the original data, t and rho. I'm just going to put them as circles. Okay, just going to put them as circles. And then I'm going to plot the new data, xe and ye. And I'm going to make them, I don't want to put, because this is like almost a continuous function now, I'm going to drop the scatter symbol. I'm just going to draw it as a line so that I see how the line behaves. I'm going to make it in blue line. Now, before I press go, I want you to think with me a little bit. How many roots does a quadratic have? Quadratic is x squared, right? Parabola. How many roots does it have? 2. Real or unreal, real or imaginary, it doesn't matter. Let's assume they're real. Okay. How many roots does a cubic polynomial have? 3. Okay. How many roots does a fourth order polynomial have? 4. Quintic, 5. Okay. How many roots does an 18th order polynomial have? 18. Okay. What did we know about a root? What does the root mean geometrically? It's when the curve crosses the x-axis. You get a root. Okay. So for a parabola, how many times does it cross the x-axis? Twice. For a cubic, because it has 3 roots, it's going to cross. For an 18th order polynomial, how many times does the polynomial have to cross the x-axis? 18 times. Okay? Now, some of those roots are going to be imaginary, so we're not going to see that crossing. But it's trying to. It's trying hard to cross the x-axis because it needs to have those roots. Otherwise, it won't exist. So could you use that to explain why we got a negative value? So when you cross the x-axis, you change sign. Why are you more likely to cross the x-axis with an 18th order polynomial? Because you have 18 roots. You have 18 times more opportunity to cross the x-axis than a straight line or than a quadratic, right? So let's see. This is exactly what's happening. So you see the polynomial initially tries to go up a little bit, but then behaves appropriately. And then it's trying to cross, it wants to have a bunch of roots, okay? And it couldn't resist it. At the end, at the last 2 data points, it crossed the x-axis, gave you 1 root, crossed another time, gave you another root. And that's what gives you the negative value. It still passed through the input data, exactly, because that's how we built it. But in between, you have no control over how it's behaving. So, bottom line is that the fact is high-order polynomials, high-order interpolants become oscillatory. Why do they become oscillatory? Because they have so many roots. They need to cross the x-axis. And you have no control over their behavior between any 2 given data points. They might oscillate 5 times and then go back. So in between any 2 data points, you could have like 10 oscillations here. And you still match the 2 data points. You still pass through them. But the behavior in between is unphysical, unrealistic in this case. They are a bad idea. In fact, anything higher than 3rd order is going to be a bad idea. Okay. Now, why did I go through this exercise and pain? Is to show you this, to show you that you don't use high order polynomials. By the end, by Thursday, I will show you in really the best of the cream of polynomial interpolants, which are called cubic splines, which are really the nicest thing ever. But this exercise is to demonstrate to you that high-order polynomials are a bad idea. Okay. So let's go back to the slides and try to summarize what we've done so far. Okay. So polynomial interpolants can be oscillatory, especially the high-order ones. In general, you want to apply a low-order polynomial interpolant locally. So if you have a lot of data points, you might be tempted to apply a high-order interpolant over the entire data set. Don't do that. either do a linear interpolant, a straight line interpolant over the entire data set, or locally do high order interpolants. If you want to do a quadratic, pick 3 points locally and do a quadratic interpolant around those. It becomes a programming nightmare to figure that out. But if you insist of doing it, you have to then kind of do the logic in your coding to find the 3 closest data points to where you want to interpolate and put a quadratic there or a cubic at best. Okay, so because this is very annoying to do, like I said, programmatically, we will eventually resort to what we call splines, which we will discuss next. But I want to just illustrate the idea to you. So this is, again, the data of temperature and density and a bunch of other properties for air. So let's say you want to, so this is the same data that we plotted, but it has more information. So there's temperature, there's density, and there's diffusion coefficient or heat diffusion coefficient, and there's viscosity. So let's say you want the viscosity or the density at 412. If you want to do a straight line, you pick 400 and 450. You do the interpolation between those 2 points, right? So you have to do it manually. If you want a quadratic, you have to pick 3 points. You can pick 400, 450, 500, or 350, 400, and 450. There's not really a preference. The closer the data points are to your target data point, the better, obviously, because you have more accuracy there. If you want to do a cubic, you would need 4 data points, right? Then at 412, you're here. You pick 350, 400, 450, 500. But you have to do that manually. If you were to fit an interpolant through the entire data set, like we just showed, it's going to be highly oscillatory. You're going to get unphysical values. It's a bad idea. Don't do it. And in fact, Python, that warning from Python, it said it's poorly conditioned because of this. And think about it. Like, think about how many roots the polynomial has to go through. And just the sheer round of error involved in x to the power 18 or x to the power 50. Like, that's going to be a huge number. And the coefficient is going to be a very small number. And there's a lot of round off going on. So you lose accuracy. You lose any usefulness of that. So don't ever do high order interpolants. Anything higher than 3 is going to be a bad idea. Okay, so I have, I guess, 10 minutes to introduce splines. Okay, now I want to go back to the point of why I changed the nomenclature, linear interpolation versus interpolation to a straight line. In my mind, when I think of linear interpolation, I'm thinking of the system of equations that governs the coefficients. And what we did so far, all those systems of equations were linear. So in my mind, that's linear interpolation because the model equation results in a linear system of equations for A0, A1, A2, and so on. So then, if you're talking to me, telling me linear interpolation, I'm like, what do you mean? Like, do you mean straight line, cubic? Someone might tell me, well, cubic is not linear. Well, no, it results in a linear system of equations. But the model is cubic, sure, it's nonlinear. So that's why I'm very specific. I say interpolation to straight line, interpolation to quadratic, to cubic. So then there's no ambiguity about that. Okay? We will see the same thing in regression. Linear regression versus nonlinear regression. But linear regression, you can put a polynomial and get a linear regression model. So then what is nonlinear regression? Is a quadratic interpolant a nonlinear interpolation? We're going to see nonlinear interpolation too here. And so it's cleaner to say interpolation to straight line, interpolation to a quadratic, interpolation to a cubic. Then you're specific and you're very clear about your argument. Okay. We'll start with splines. Very likely we're going to need a little bit of time for next lecture. So to resolve the issue of having to figure out the 3 neighboring points or the 4 neighboring points to put a quadratic or a cubic. Obviously, quadratics, cubics, they're going to give you more accuracy. They give you some nice variation in the data. They're desirable. Okay, they're higher order. They're desirable. They give you nice curvature. But it's very annoying to try to program your way around finding 3 data points or 4 data points around the point of interest. You change that, you have to go and sort through the array and figure out. It's doable. It's not impossible. It's just a little bit tedious to do that. So cubic splines come to the rescue. And not only that, cubic splines challenge the idea that so far we did for 2 points you can put a straight line, for 3 points you can put a quadratic, for 4 points you can put a cubic, and so on. But they challenge the idea and they say, we are going to put a cubic between every pair of points. Like, huh? Well, is that possible? So the reason we chose the number of points previously, it was to give us more conditions on the coefficients. So let me give you this. Let me give you the equation. So here's the equation of a cubic. ax plus b, ax cubed plus bx squared plus cx plus d, okay? So we have 4 unknowns. But I want to put this cubic between 2 points. The question becomes finding those unknowns. I need 4 conditions. Passing the cubic between the 2 points is going to give me only 2 conditions. Okay, agreed? But I can find other conditions without having to rely on the points. What if I say something about the derivatives of the function at those points, or the second derivative? So it becomes a matter of just finding ways to find more conditions to find the unknowns, right? So yes, I can fit a cubic which has 4 unknowns between 2 points, but I have to have more conditions to be able to get enough equations for all of these unknowns. Okay, so here's how cubic splines work. We're going to take this example. We have 1, 2, 3, 4 points, okay, and then we'll generalize. We have 4-point pairs, x1, y1, x2, y2, etc. And we want to put a cubic between each pair of points. The first cubic here in red is a1x cubed plus b1x squared plus c1x plus d1. The second cubic in green is a2x cubed. So I'm changing the index on the coefficients because this is going to be a different cubic than this one. So the coefficients are going to change. And same here for this purple one. The third cubic is f3, and it's a3x cubed plus b3x squared, and so on and so forth. Okay. So for these 4 points, we are able to put 3 cubics, or we want to put 3 cubics. In general, for n plus 1 points, we can put n cubics. We're going to call them splines from now on. Okay? So in general, for 4 points, I can put 3 splines. For n plus 1 points, I can put n splines. Now for each spline, how many unknowns do I have? 4. The A, B, C, and D for each spline. So in total, I have 4 times n unknowns. So n splines, 4 unknowns per spline. So we have 4n splines, 4n unknowns, sorry. And therefore, we need 4n conditions or 4n equations to be able to solve for all of those unknowns. Okay. So what you're responsible for here is knowing all of those conditions and be able to just work the conditions. We're not going to solve the system of equations. Python will do that for us because it's still quite tedious. But what you need to know is how these splines are built. So the first and easy thing to do is that the first and last splines, they must pass through the first and last data points. So that gives me 2 conditions, right? First point and last point. For the first spline, last spline gives me 2 conditions. Next, at each interior data point, like take this one, there are 2 splines that connect to it. And each spline must pass through this point. So the red spline must pass through x2, y2. The green spline must pass through x2, y2. The green spline must pass through x3, y3. And the purple spline must also pass through x3, y3. So at each interior data points, I can hit 2 splines, so 2 conditions. How many interior data points do I have? N minus 1 interior data points, right? Since we had n plus 1 data points, n plus 1 minus 2 gives us n minus 1 interior data points. So for 4 total data points here, interior is 2 data points. So in general, for n plus 1 data points, we have n minus 1 interior data points, times 2 constraints per data point. So that gives us a total of 2n minus 1 constraints. So I know this might be hard to kind of follow through right now, but go ahead. But you will have to repeat this at home to go through these conditions. Okay. We're still not close. We're still missing a few constraints. At each interior point now, it's not enough because we need 4n equations. So far we have 2n minus 2 plus 2 constraints. So we have 2n. We need 2 more n conditions, okay? 2n more conditions. Now we start with the derivatives. We say at each interior point, the first derivative of adjacent splines must be equal to ensure that they're continuous even in their derivatives. So the derivative of the red spline at this point must be equal to the derivative of the green spline. So it gives you one condition. Derivative of green spline must be equal to the derivative of the purple spline, gives you another condition. So in total you have n minus 1 conditions because you have n minus 1 interior points, okay, for the derivatives. Okay, still not enough. Let's go and match the second derivative. Again, I'm after conditions. We passed them through the points. That wasn't enough because I'm putting a cubic between 2 points. If I was putting a cubic between 4 points, that would be enough. But I'm not. I'm putting cubic between 2 points, so I need more conditions. So I'm going to put conditions on the first derivative. Same thing for the second derivative. Match the second derivatives at all interior points. You have n minus 1 interior points. One condition for each interior point. So derivative to the left equals the second derivative to the right. So you get n minus 1 constraints. We're still missing 2 constraints. Then you say at the end points, the second derivatives must be equal to 0. So that you're not looking at the slope, you're looking at the convexity of the curve. And naturally, what we call the natural spline is you set the second derivative to 0 at those endpoints. And then you count all of this. You have 2 plus 2n minus 2, that gives you 2n, plus n minus 1 plus n minus 1, so 2n minus 2, and then plus 2, that gives you 4n. Okay? 2n plus 2n is 4n. Okay. So here's how this works. The first and last splines must pass through the first and last 2 constraints. So f1, the first spline at x1 equal y1, and the last spline, f3 at x4, must be equal to y4. So those are 2 conditions. At each interior data point, there are 2 splines. The 2 splines must pass through that point. So here's what you get. So at x2, y2, f1 at x2 must be equal to y2, and f2 of x2 must be equal to y2. At the other point, f2 at x3 must be equal to y3, f3 at x3 must be equal to y3, so on. Okay. Now you go after the derivatives. F prime 1 at x1 at x2 equal f prime 2 at x2, and f prime 2 at x3 equal f prime 3 at x3. You match the derivatives, first derivatives. You also match the second derivatives, and then you do the second derivative at the endpoints. You need to know this. That's all you need to know about splines. Okay, so on Thursday, we'll do this in Python. Okay, I'll see you on Thursday.